Hey there, Calc 2 folks, back here with another video in our study of Chapter 11 material where we're studying the power series. And in this section, we are actually going to formally be introduced to the power series, as well as some concepts of the power series with respect to its convergence, right? If we just take note, what brings us here is our study of the nth degree Taylor polynomial, right? If we recall from the previous section, the nth degree Taylor polynomial is given by this value here. And let me bring this over. I didn't realize we were so out of screen. All right, here's our nth degree Taylor polynomial, right? Centered at this value of x equal to a, right? And if we consider the case of an nth degree Taylor polynomial where the value of n heads off to infinity, it's going to be a special case of what is called a power series, right? If the value of n gets replaced with infinity in our Taylor series, we are going to have a special case of power series known as a Taylor series, right? If n gets replaced with infinity in our Taylor polynomial, we'll have a special kind of series called special kind of power series known as a Taylor series, right? And what this section introduces us to is the concept of a power series, as well as the concept of when a power series is convergent, which is known as the interval of convergence for the power series, right? If we jump into the definition of a power series, this is what we define, right? As well as defining out what we mean by an interval of convergence, right? By definition, a power series is an infinite series in this form here, right? Where we did see this form presented in the case for a Taylor polynomial, right? Certainly, we didn't have the series head off to infinity, but the argument was very similarly presented. What we have here is some coefficient factor that's an argument of k times this quantity x minus a raised to the kth power. All right? We take note that this series does involve a couple of values within it, right? A couple of variable values. First of all, are these values we might point out as a and c sub k, right? A and c sub k really represent real numbers in the series, whereas x is going to stand for a variable value in the terms of the series, right? The value c sub k is called the coefficient of the series, right? And a, the value a, was known as the center of the series, right? In a Taylor polynomial, we had a very specific statement for this coefficient, right, of the series, and we were considering being centered at a particular value in our Taylor polynomial. All right, so we see, again, a very similar format here for defining a power series, right? We can see that the Taylor polynomial relates itself to the terms of the series, most certainly, right? And furthermore, we can go on to note the values of x where a power series converges, right? One thing we are going to note is that in this series, x is going to play the role of a variable value. And depending upon the values of that variable, this series is going to converge, right? And at the values of x where it is convergent is known as your interval of convergence, right? And the distance from the center at x equal to a to the bounds on this interval of convergence is actually known as the radius of convergence, all right? So here we define out what it means to be a power series, and then we do follow that up with what we mean by the interval of convergence and this idea for radius of convergence. All right. What we might best do here is to look at an example involving these terms, right? If we bring into view here an example, we might consider this power series given here. Right? If you take note in this power series, we definitely see the form presented above. If I scroll back up to bring that form into view, here we have this series starting at k equal to 2 and continuing up to infinity, right? Where our coefficient of the series is this first factor, 2 to the kth divided by k. This factor here is the coefficient of our series times this quantity here, this x minus 3 raised to the kth power, where we have replaced the value of a with the value of 3, right? Meaning that that 3 is the center of this series. It's where we think of this series, this power series, being centered. This quantity here is the coefficient c sub k in the above form. The value of 3 is the center, and what we notice is x is a variable value in this series. It's going to remain a variable as we look at the terms of this series. All right? If we bring some of this into view here, right? Again, we point out that we do assume this form where a is 3 and c sub k is equal to this quantity, right? Where I believe now I've expanded to the terms, right? Expanding the series into its corresponding summation, right, does produce this result here, right? Where you notice what we end up obtaining, right, with the expansion of this power series, right, is going to be a polynomial function. It's going to actually be what we think of as an infinitely long polynomial function, where the variable in that polynomial function is going to be the value of x, right? As we had noted in these series, x plays the role of a variable in that series. It's a variable that sticks around and is part of the summation. This value c sub k becomes some constant coefficients in the series, some constant coefficients for this polynomial that depend upon the value of k, and the series centers itself, right, in each of these terms around this value of 3. Right? We can see that in this expansion. Right? And what this does produce, right, as we pointed out, this infinitely long polynomial function. Right? Now, what we go on to note is whether or not this series converges, right? Really what's going to help us determine whether this series converges is going to be the behavior seen in each of these terms as we head off to the value of infinity. And that behavior depends upon the value of x in each of the terms, right? Depending, as we noted, this is going to be this infinitely long polynomial, which will develop constant terms as soon as we substitute a value of x into each of these terms, into all the infinite terms, right? And what that value of x will do will either cause the series to add up to a divergent value, or what that value of x will do will cause this series to add up to what we call a convergent value. It'll become, for certain values of x, it will be divergent, and for certain values of x, it may be convergent, right? Now, the values of x, where this power series converges, forms what is known as the interval of convergence, right? As we had noted, depending upon x, we will see convergence or divergence, and there can be at times a whole bunch of x's, right, centered at this value of 3, where we happen to see convergence, right? At those values of x, centered at the value of 3, they form what we call our interval of convergence, right? And the way we actually determine the interval of convergence, right, for a given power series is that oftentimes we rely on what we call the ratio test for convergence. We rely on that test for convergence we learned at the end of chapter 10, right, which is this ratio test for convergence, and analyzing the result of it when we apply it on this power series. All right, what do I mean by that? Well, let's consider applying the ratio test to this power series. All right, if I apply the ratio test to this power series, right, first of all, we would note that our value of a sub k would be this argument inside the series, which does imply that a sub k plus 1 is going to be this argument times this argument, right, in our series, where what we've done is that every value of k in a sub k, we've replaced it with the argument k plus 1, right? Where with our work with ratio tests in the previous section, we do know how that's going to be handled here, right? 2 to the k plus 1 power becomes 2 times 2 to the kth power. K plus 1 is simply just still k plus 1, but x minus 3 to the k plus 1 simplifies into x minus 3 times x minus 3 to the kth power, right? It expands into this argument here, we might say. Where now in the ratio test, what we're going to want to do is look at the absolute value of the ratio of these terms. A sub k plus 1 over the value of a sub k inside in an absolute value symbol in the test. I do note here, I do consider, first of all, the ratio before I jump into the absolute value. If we look at the ratio of a of k plus 1 to a of k, right? If we consider simplifying that as we did back in the case for ratio tests, this does simplify to this argument here. 2 times k times the quantity x minus 3 divided by k plus 1, right? Where if we now put that into our ratio test, right, the value of r that we have in our test, right, ends up equaling the limit as k approaches infinity for the absolute value of this argument. It is going to be the limit as k heads to infinity for the absolute value of that argument, where you will notice that absolute value will distribute itself across the factors in the numerator and the factors in the denominator. And note, for values of k here, k is going to be an index back in this example that starts at 2 and goes off to infinity. So 2 to the k, starting at 2 and going to infinity, will always be positive, and so will the quantity k plus 1, right? So when the absolute values apply themselves to this argument, they aren't needed for 2 to the k and k plus 1. The only argument that could potentially, right, have the absolute value symbols change a negative into a positive result would be on the absolute value of x minus 3. So we are going to have to leave those around that quantity, where if we think then for a moment about that quantity given by the absolute value of x minus 3, when we consider the limit as k heads to infinity, this is just a limit in terms of k. The quantity given by this absolute value of x minus 3 in terms of k is a constant. And it can actually be brought out in front as a constant multiple, where now we just become interested in the limit as k heads to infinity for, in this case, 2 times k over k plus 1. And from our fundamental rules for limits at infinity, this rational form will produce the result of 2 for its limit. So in the end, what we get for the value of r is that r is equal to 2 times whatever the absolute value of x minus 3 would be, right? The test value we have in the ratio test known as r will take on this form that now depends upon the value of x, all right? Put a period there. We'll come back and take note that in the ratio test, a series is absolutely convergent when its value of r is less than 1. Up here in this ratio test, the value of r we just calculated was given by 2 times the absolute value of x minus 3. So in this case, the series where r equals this, right, is absolutely convergent. Right? is absolutely convergent when this value of r given here is less than the value of 1. All right? Which does have some implication. All right? It implies then that if we multiply both sides by 2, that absolute value, or careful there, divide both sides by 2. If I divide this side by 2 and this side of that inequality by 2, that will imply that the absolute value of x minus 3 must be less than 1/2. Where if I now apply my understanding of absolute values equation, or I should say the case for solving absolute value inequalities, right? This argument x minus 3 inside the absolute value symbol must be between negative 1/2 and positive 1/2 in value, right? Where if I solve now for x by adding 3 to all sides of this, to the two outsides and the inside, adding 3 to negative 1/2 produces 5/2, and adding 3 to 1/2 produces 7/2 in value, implying that the value of x we're interested in is somewhere between 5/2 and 7. Now what this is here, folks, this is the beginnings for our interval of convergence. This tells us that certainly x, or when x is between 5/2 and 7/2 in value, right, we have values of x where this polynomial function, right, this infinitely long polynomial function is convergent in value. Now, I will tell you though, when you obtain a interval of convergence that is finite in length, from the ratio test here, right, where this all came about from r having to be less than 1 to be absolutely convergent in the test, you do have to test these individual bounds. What you will notice is these individual bounds, 5/2 and 7/2, were values of x back here in our test that actually caused the value of r to equal 1. 5/2 caused it to equal 1, and 7/2 will cause it to equal 1. Both of those will cause this absolute value to be 1/2 in value, and when multiplied by 2 will be equal to 1 in value. And if you think back to the ratio test was inconclusive in its results when that value of r was equal to 1. So these boundaries of 5/2 and 7/2 actually cause an inconclusive result in the ratio test. So what we need to do with these two results that cause this inconclusive result found on the boundaries of this interval, we need to test those individually in our power series. We need to come back here to this power series and consider allowing this value of x to be 5/2 in value and let it be 7/2 in value. And you will see that is what we do here. All right? I do open this with a note. We say note, when r equals 1 in value, right, the ratio test is inconclusive. In this case, r equals 1 when x equals 5/2 and when x equals 7/2 in value. So these bounds on x may be a location where the series is convergent, right? 5/2 or 7/2 could potentially be locations where the series is convergent. And to test these bounds, right, for x, we must rely on some other tests of convergence. All right? The ratio test is not going to work for us here in trying to test those bounds because it will cause r to equal 1 in our test. So if we take note, if x equals 5/2, the power series is actually expressed as this series here, right? Replacing the x with 5/2 would produce this argument, which we could simplify into this here, this argument, which you'll notice is an alternating series, right? We have that -1 raised to the kth power in there. In fact, we can think of this argument here being -1 to the kth power all over 2 to the kth power, right? That would become this here, this argument here. And then what you will notice there is that that 2 to the kth and that 2 to the kth will cancel, leaving you with negative 1 to the kth divided by k. This series here is an alternating series. In fact, you can notice that it is the alternating harmonic series. All right. Well, what do we know about the alternating harmonic series? It's convergent by the alternating series test. All right. This here is a convergent alternating series. If we were to take the limit as of 1 over k, that would equal 0 in value, and that is the result that produces confirms convergence in an alternating series. That is the convergent result from an alternating series test. So at x equal to 5 halves, that boundary, the series is also convergent, and we're going to have to note that in our final interval. As for once we have 7 halves, we will have a similar looking series, right, produced here, but it will not be alternating. In fact, using similar properties here, we can simplify this into a similar looking statement, but it's not alternating. Canceling the 2 to the k's in the numerator and denominator, we do produce this, what we should recognize as a harmonic series. And what do we know about harmonic series from the integral test is that they are a divergent p-series, right? This is a case where p equals 1, and that is the case for divergence in a p-series. The harmonic series diverge. The alternating ones converge, but the non-alternating cases diverge, right? So at x equal to 7 halves, this series actually is divergent, right? It is this divergent harmonic series. So if we put that all together to denote our interval of convergence, the interval of convergence then is going to be this interval here, from 5 halves to 7 halves, including the 5 halves, but excluding the 7 halves in value. All right. Keep in mind where that series began was back here in the ratio test, where we knew this as the cases for x that caused r to be less than 1. But at 5 halves and 7 halves, we have inconclusive results in the ratio test. So we have to test those individually, and we do that below here, where we determined 5 halves converges, but 7 halves does not as a value of x. So we include the 5 halves in that interval, and we remain excluding the 7 halves in that interval. All right? And what this describes is our interval of convergence, folks. All right? Even more so, since we are centered at 3, you will notice halfway between 5 halves and 7 halves, this is 2.5, this is 3.5 in value. You will find your center of 3, and the distance between 3 and these bounds is 1/2 in value, and that describes your radius of convergence. All right, folks. So that is what we're looking at here initially in this definition, up here at the top. Right? We are exploring these series known as power series, these series that assume this form, Matt, right? Where you have this common factor of x minus a raised to the kth, where a is some value of x that the series centers itself on, right? And c sub k is some coefficient of k. It's a real number in the series, right? Down here, it's these values of 2, 8/3, 4, 32nd fifths, and so forth, right? It was these values that were determined, right, to be the coefficients for the different degrees of x found in this polynomial function, this infinitely long polynomial function. And they depended upon what index we were at within our series. They were determined by this leading coefficient c of sub k. All right? At values of x, then, where this power series converges is known as your interval of convergence. And that distance from the center to those bounds on this interval are known as, well, that distance is known as your radius of convergence. All right? Now, with respect to intervals of convergence and radius of convergence, there really are three cases that can occur depending upon that radius of convergence. All right? The first of those cases, right, is you could have a radius of convergence that is actually infinite in size. In that particular case, your interval of convergence would actually stretch from negative infinity to positive infinity in value. All right? When you analyze your convergence of your series, you may encounter convergence that happens at all values of x. All right? That would give you, again, this infinitely long or large interval of convergence, everywhere from negative up to positive infinity. That is one result that could occur. Another result could occur is that you get a finite interval of convergence. All right? A finite interval of convergence happens where r, this radius of convergence, is somewhere between 0 and infinity in value. All right? Meaning that the power series only converges over values of x described in some interval, where this is similar to what we saw happen above in our previous example. Our interval of convergence was some interval of values, right? Our radius of convergence was finite in value. It was 1/2 in value, right? Which gave us this interval, right? And one thing we do have to note there, and I do take note, is note in the case of the bounds, right? Or in this case, the bounds should be tested individually for convergence. When we're looking at these bounds on this interval, and notice these are the bounds, this is a minus r and a plus r are our bounds on this interval. That is where we are centered at, plus or minus our radius of convergence. And what I have noted here is that we can either have them grouped between parentheses and not included, or they could even be included. It really depends upon what is their result when tested individually, right? And you should look at testing them individually as we had done in this previous example. All right? That's the second case for what could happen. And then the third case for what could happen here, right, is you could actually get a radius of convergence that is 0 in size, right? R could end up equaling 0. You have nothing in size for your radius of convergence. What this does mean is that the power series only converges at its center, right? It only converges at a value of x equal to a, right? Folks, those are, again, your three different results that could occur for your interval of convergence. Either it's indefinitely large in size, it's definite in size where the radius of convergence is bigger than 0, and in that case you definitely want to make sure you test your boundaries also for convergence when using the ratio test to determine the interval size. And then the third case is you could have a radius of convergence that is nothing, meaning that power series converges only at its center. All right? Let's look at one more example here, another quick one. Let me bring this up into view. Let's consider the convergence of this series here. All right? This power series. All right? If we consider the convergence of this power series, now notice it is a power series. It is some coefficient of k times this common factor x minus 1 raised to the kth power in the series, where from the ratio test, a sub k would be equal to x minus 1 raised to the kth over k factorial, and a sub k plus 1 would be x minus 1 times x minus 1 raised to the kth all over k plus 1 times k factorial, right? We've done this a couple of times already with ratio tests, so we should begin becoming familiar with how a sub k plus 1 does behave and how we might want to express that so that in our next step here, when we consider their ratio, right, we have results that cancel nicely. Let's see, can I get this? There we go. right? When we consider the ratio of a sub k plus 1 to a sub k, right? Multiplying by the reciprocal of a sub k, we get some nice canceling happening. And we get this end result, x minus 1, evaluated at k plus 1. Where now if we consider our value for r, what's going to be the limit as k heads to infinity for this quantity x, the absolute value of x minus 1 over k plus 1, the absolute value of a sub k plus 1 over a sub k. That absolute value is only going to apply itself to x minus 1. With regards to k plus 1, k is always greater than 0. It starts at 0 and gets bigger, so that it's never really negative in value where those absolute values are needed. So the absolute values really only apply to the x minus 1, right? If we think about now the limit in terms of k, x minus 1 is a constant, and it can bring itself out in front of the limit, where we no longer need the absolute values around the k plus 1. And if we now consider the value of this limit, we should note that that value of the limit is 0. All right? As that denominator grows without bound, the value of the ratio heads to the value of 0. The limit's value is 0. So the absolute value of x minus 1 times 0 will always be 0. Which means it doesn't matter what you have for a value of x. X can be any number from negative infinity up to positive infinity, and regardless of what x is, r will always equal the value of 0, right? And since the ratio test is absolutely convergent when r is less than 1, and r will equal 0 for all values of x in this case, our power series in this case must converge then on this interval from negative to positive infinity. Right? What we have occurring here in this case is we have a radius of convergence that is infinite in size. We have this situation back here, right, given by case 1 for the result of what our radius of convergence could do. Right? This is the first type of interval of convergence we could encounter for a power series. All right? And we can see how that came about. That came about from considering our value of r in the ratio test here and seeing that regardless of what x is, r will always equal the value of 0 because this limit here is always equal to 0. And in the ratio test, if r is less than 1, you have the case for convergence, and r is always equal to 0, well then it doesn't matter what x is. R will always be less than 1, and you will see convergence at all values of x, which is along this entire interval, folks. All right? So keep in mind, folks, we are going to be looking at the case for power series. And what brings us to power series, again, if we go back, and where we're heading into our next section, is understanding that what we're going to be looking at in the next section is a Taylor series. All right? A Taylor series being really a Taylor polynomial that is infinite in its size, that uses an infinite number of terms. And when we have a Taylor polynomial that is infinite in size with an infinite number of terms, it does fit the format of what we call this power series, right? And this concept of convergence, right, in this power series is going to also play a role in talking about in discussing the convergence of a Taylor series. Right? So that's what we are going to come back to, folks. We are going to return to looking at the Taylor series, and these ideas of power series are going to come back and play a bit of a role there. Right? And we're on the cusp of finishing our material here, folks. So hopefully I will have an assessment out to you very soon, and I hope you're hanging in there, and I hope you're following along with these videos and you're staying on top of them. And like I said, we are almost done here with Chapter 11 material. We have to talk about Taylor series and working with Taylor series a little bit. And those are the last two sections here. So I will see you then.